Hi class, I am going to pretty much summarize where we are up to this point today in this video. So we're starting the new section, hypothesis testing. This is kind of really big deal. It's kind of the main point of this statistics class. So we'll do a very brief overview of kind of everything we've studied so far. Okay. So really what's been happening is that we start off with a population. And in this population, we have certain characteristics, right? We call them our parameters, P for population. So our characteristics that we're interested in from our population are our mean and our standard deviation. Mu and sigma are our parameters of the population. They are the characteristics that we are interested in that describe our population as a whole. Now, a lot of times our population is too large to talk about. For instance, if you're talking about living things, their population is always growing and shrinking, right? Things are always being born and dying at the same time. If I wanted to find out some information about bees, it would be pretty hard for me to gather every single bee in the world and weigh them, measure them, analyze them, what have you, right? So an easier thing that we can do is we can gather a sample. Okay, so our sample is gathered from our population. Ideally, it's gathered randomly. Randomness helps us to make sure that our sample represents the entire population. Okay, if I'm interested in people who attend Skyline College, I'm not going to only look at the female students because there might be some differences between female students and male students. I need to get a sample of all of the students, right? Similarly, I wouldn't gather only math students to talk about the general Skyline student. I would want to talk to a random sampling of all students so I get a sample that is representative of the population. Okay, so in our sample, we have certain characteristics as well. We do not call them parameters, we call them statistics. Okay, our statistics, right, our characteristics from our sample are X bar and S of X, S sub X, right? They are analogous to the same characteristics in our population. X bar and mu are kind of the same thing. S of X and sigma are kind of the same thing, right? Although they're different because one is for the population and again one is for the sample. Okay, a good sample will represent the population. Our X bar should give us a pretty good idea of what mu looks like, and our S of X from our sample should give us a pretty good idea what sigma looks like from my population, right? So the goal is to use stuff from my sample to be able to talk about my population. And again, the way that we want to do that is to make sure that we have a random sample. A random sample will ensure that we have a sample that is representative of the whole population. Okay, so randomness is how we ensure representation of the whole, right? So this is kind of what we started talking about on the first week or two, and then we started to talk about what to do with a sample, right? So once we have a sample, we want to organize this sample, okay? We want to organize and analyze our sample, right? We're interested in things like what is the center, things like what is the spread, and what does this graph look like once we plot it out, right? And this kind of leads us to what we were calling the distribution, right? If we know what the distribution looks like, we know what the graph looks like, we know what the data looks like, and we can start to find things like probabilities. We could talk about the skewness, whether it's symmetric, the range of values. We can look at z-scores. So that was the organization and analysis portion, right? So once we did that and we learned how to find probabilities and things like that, that's when we can start to do what we call inference. Okay, inference is where we are at now. Inference are the tools that we use to be able to take the information from the sample and talk about the population. So we have two kinds of inferences that we've been dealing with. One we did last week and one we're going to do this week. So last week we talked about confidence interval, and this week we are going to be talking about hypothesis test. There are several different types of hypothesis test, so we're just going to go over the basic methods of hypothesis testing, and before the final we'll talk about the more advanced methods, the other methods of hypothesis testing, like having two samples, comparing things that are categorical instead of numerical, right? Things like favorite colors. Right now we'll be looking at things like proportions and means, right? So once we get some information from our inference, we can then talk about the population, assuming that we have a good sample. Okay, so we can talk about our population. So that's kind of where we're at now, is we know how to gather samples, we know how to organize those samples and look at sort of what the data is telling us, and now we're going to use that data to make an analysis to talk about our population as a whole. Okay, so let's get into the nitty-gritty and we'll talk about hypothesis testing. Okay, so let's get into the basics of the hypothesis test. Hypothesis testing is for when we believe something to be true. We go out, we collect some data, we look and we analyze the data, and then we figure out whether or not what we think is true is actually true, or if something different is going on. Okay, so the hypothesis test is like writing a report. Okay, it's very similar to the scientific method when you are trying to prove some sort of scientific theory. So for the hypothesis test, there are two things there: the null hypothesis and the alternative hypothesis. So the first thing that we want to do is we want to state the null hypothesis, which we call H naught, and the alternative hypothesis, which we call H of A, right? Alternative hypothesis. Okay. H naught, H of 0, is our default, right? It's called our null hypothesis. It's what's going on if we don't think anything weird is happening. Okay, so it's the default. It's what we already assume to be true. And then from our data, we're trying to show whether or not the alternative hypothesis is true or not. So the null hypothesis is H naught. It is our default true statement. Okay, H sub A, our alternative hypothesis, is what we are testing is true or not true. Okay, so H naught, the null, that's our default. H of alpha is when we think something weird is happening. Okay, so a little bit more about the null and the alternative hypothesis. The null hypothesis always has an equal sign. Okay, the alternative hypothesis always has either a less than, or a greater than, or a not equals symbol. Okay, so null always equal, alternative always a less than, greater than, or a not equal. Okay, the second thing that we have to do is we have to state what kind of test we have. Right, so we're going to state the test type. Are we talking about a mean, a proportion, two sample mean, two sample proportion? Difference of proportions, we're not really there yet, but right now it's either a mean or a proportion, and it is going to be either a left tail, right tail, or two-sided. Okay, and whether or not I'm a left tail, a right tail, or two-sided really depends on my symbol that I'm using for the alternative hypothesis. If in my alternative I'm having a less than, it's going to be a left tail. If I'm looking for greater than, it's a right tail, and not equals is two-sided, right? So it really depends on what my proposition is. Actually, we'll talk about this when we do an example. Okay, it's kind of switched, but it really depends on how you write the statement. Okay, the next thing you have to do is we have to verify the conditions for the CLT, right? So I brought this up in the previous video that I made. When we are verifying conditions, we need to show that our distribution or our sample was collected randomly, that each element in our sample is independent of each other, and that there is a normal type of distribution. So either my distribution is normal or approximately normal. If I don't have normality, I can't use the normal distribution, which is the distribution I need to use to find all my probabilities. Okay, so remember, we're collecting a sample. From that sample, we will find the sample mean, x bar, and then we talk about how that sample mean is distributed compared to all the other possibilities I could have had for a sample mean. So basically, I'm looking at the distribution of sample means, the central limit theorem. I have to have the conditions for central limit theorem, or I cannot conduct a test. So I have to verify to my reader that I have these conditions. Okay, it's very important. Okay, the next thing we want to do is we want to state the level of significance. We call this alpha. It is pretty much the same thing that we had from our confidence intervals. I'm going to test these at certain values. They will typically be at either 10%, 5%, or at 1%. Okay, typically this is given to me in the word problem that I'm working on. They'll say test this at the 10% level, at the 5% level, or at the 1% level. We can talk about when we need to choose this for ourselves. I have a handout that is available to you guys. You can look at it. All the things I'm telling you now are basically on the handout, but we're going to have some visuals and we're going to go through an example in this video to kind of make, to solidify some of the ideas that we're talking about. Okay. So the next thing I need to do is make a graph. Okay. So I know you guys have a little bit of trouble making a graph, so we'll focus on that a lot in this video. In my graph, I need to plot either my standard deviation for means or for proportions, depending on which one I'm doing, right? Which is important from my test type, either means or proportions. I have to find my z of alpha value. I want to put that into my graph as well, because that plays a very important role. Obviously, I'll state what the alpha is. My mean value for my population, whether I'm calling that mu or p, right? It's either means or proportions. We use the right one for the right distribution we're using. And then I talk about my standard error, either my standard error for means or my standard error for proportions, depending on if I'm talking about a test of means or a test of proportions. Okay, so we also need to graph our probability. Okay, the probability of us getting a sample similar to the one that we have, and we also want to graph our rejection region, and I'll show you how to do that as well. Okay, so I have some formulas that'll help us for this, just in case you guys get fuzzy. Right, it's nice to have all your formulas in one place. So first, let's talk about the formulas for z of x bar or z of p hat. So again, these are z-scores, right? They're z-scores. So you're using the standard normal distribution, mean of 0, standard deviation of 1. Okay, so if we have a standard deviation of means, it's x bar minus mu divided by the standard error of means. Or if we wanted to write that out as a full formula, it looks like this. Okay, remember, sigma of x bar is your standard deviation for the population divided by the square root of your sample size. Okay, if I want to do it for p hat, for my z-score for the proportion that I found, right, my proportion of successes from my sample, if we're doing proportions, I follow this formula. It's very similar in form. My statistic minus my parameter, statistic minus parameter, divided by standard error, right? So if we turn that into our formula for proportions, it will look like this, right? So this is our, what we call, this is our formula for our test statistic. Okay, this is our test statistic formula, right? So this is the z-score from our sample value. Our sample mean or sample proportion is our test statistic. We are using that to test against what we are assuming to be true. Okay, so test statistic is the z-score from your proportion that you found, or the z-score from the mean you got from your sample. Next, we need to plot our z-score for our level of confidence, either this 10%, 5%, or 1% of confidence. That is a z-score. We don't know the data value for it, but we know the area that z-score will give us. So we'll need to use the inverse norm for that. Okay. If I am doing a left tail test, I will use this formula because this will give me 10% of the area on the left side of the graph. If I need to do a right tail test, okay, I will use 1 minus alpha because this will give me 10% or 5% on the right side of my graph. And the area that this covers, either from this value, this z-score to the end on the right, or this z-score to the end on the left, is called our rejection region. Okay, it's a very important region. That's why we have to graph it. It tells us what's going to happen, and it tells us the results of the test. And the next thing we have to find is the p-value. Okay, the p-value, it's different from this p-hat or my actual proportion of p, right? It is a probability value. It's the probability of getting the test statistic that I got, right? Either the test statistic or the actual sample mean or sample proportion, assuming that my null hypothesis is true. Okay, so basically it's the probability that what actually happened is likely to happen, assuming that this is true. Okay, now in order to find this, we're going to use the normal distribution, and I have a formula for that for you. Okay, so our p-value is the probability that we get z-scores larger than the z-score that we got, assuming that the null hypothesis is true. Okay, so how would I find this? This would be a right tail test because I have my z-score, and I'm looking at the probability of all the z-scores that can be more than that one. More than that one. So this would be how I would find a right tail test. Normal CDF, the first thing I put is my z-score for my test statistic, 10 to the 99. My mean, my standard deviation, in this case it should be 0 and 1. And if I want to do a left tail test, then I do it in this manner, right? I have my lower value, my z-score, and then this should be 0 and 1. I left it as mu and sigma of x bar because we can use these with our data values, but this would change. Instead of z of x bar, this would be x bar, and this would be x bar or p hat as well. Okay, so we can do this with 0 and 1, the standard normal, with z-scores, or we can use our actual original data values and have x bar here, and then our mean and our standard deviation for the distribution, right? So you have some wiggle room there as far as how I want you to answer, but I will be asking you to change things into z-scores. I always change them to z-scores myself, so it's better if you learn how to do it with z-scores and with 0 and 1. Okay, that's a better option, right? That's how you're going to see things happen in this class, up to 10 and 99. That's the most likely thing to happen, although you can use your data values instead of x bar and then your mean and your standard deviation for your distribution. Okay. Next we have our conclusion, our summary. In our conclusion and our summary, we want to compare our p-value to our alpha value. Okay, our p-value should be somewhere close to this alpha value. It's going to be either more or less, and then that'll determine our decision whether or not we kind of keep this thing or we switch our idea to the alternative hypothesis. We want to state this conclusion in terms of the problem. Okay, we don't want to just say p-value is this, so this, right? We want to talk about what's happening to our problem, because you got to remember, this is like writing a report. Okay, if you're reading a scientific paper, they're going to talk about p-values all the time, but in context. If you have to write a report to somebody, most likely a boss, you need to write it in context, right? So make sure you know how to put these things from the p-value world into talking about what it means in terms of your situation. So again, I'm just glossing over everything. Okay, I suggest you watch this video a couple times, and we're going to do an example as well, so you can relate all the things that we're talking about to an actual example. And I'll do some write-ups, and I'll post some PDFs of the write-ups to our website as well. Okay, so we have one more thing to look out for, and that is for possible errors. Okay? So you got to remember, this is statistics. Statistics is about collecting data and looking at the data and making the best guess possible. It is very possible that you have errors in your decision making. Okay, so we want to talk about the type of errors that we made. Okay, and this isn't like, oh, I calculated this wrong, or I did this incorrectly possibly, or maybe I got a bad sample. We want to talk about errors in our conclusion. Okay, it's possible that my conclusion is an error, so it might be, my conclusion might be this thing instead of what I concluded before. Okay, so these last two are very, I'll say cookie cutter-ish. They're kind of the same all the time. You just really need to compare your p-value to your alpha value and say what that means. And then your possible error is, hey, I probably made an error, so this other thing is probably what's going to happen if I was wrong. Okay, so let's get down. Before we do an example, I want to show you a graph and where all of these things come into play on the graph. Okay, and we'll talk about these things more so for a right tail test. So let's kind of set that up before we look at the graph of that. Okay, so we're going to do an example of a right tail test. We're just going to look at the graph of one, and then we'll do an actual example. Okay, so if I'm doing a right tail test, then I'm assuming that my null hypothesis, my mean, is equal to whatever they're giving to me in the word problem. My alternative then would be that my mean is actually more than the given value that they're telling me. Okay, I would need to verify my conditions, talk about what kind of test it would be. It would obviously be a right tail test of means. In this case, if I'm talking about mu's, right, if it was p-values, then it would, or if it was it would be a right tail test of proportions, but we're going to assume it's means here. When I do my graph, I want to graph my test statistic. Okay, remember that's a z-score that's coming from my x bar value. Okay, being lazy here, but this should be z of x bar. I need to put my my critical value. Okay, z of alpha value, z sub a. Okay, that's my critical value. That tells me where my critical region is. Once I do that, I want to find my p-value and graph that as well. Most of that work is actually done in plotting this test statistic. Once I do the test value, the test statistic, and the critical value, I can kind of talk about what's going to happen as far as my conclusion is concerned already. But it's nice to put the p-value in there as well. Okay, so let's just look at this graph real quick. Just a general overview of not a hard in cement sample example, but just, you know, what it would look like if we had something of this nature. So we come over here to graph. Let's say that I have a normal distribution that looks like this. My mean is 0, standard deviation of 1. Okay, this is the z-score for my example test statistic. This is the z-score for x bar. Here I'm saying I have a standard, not standard deviation, but a z-score of 1.2. And then it's a right tail test, so I'm looking at the area after this value. Okay, and here I have the probability, I have the area that's after this value. This is my z-score for this z of x bar. So this is the probability of all the z values larger than the one that I have here if my null hypothesis is true. So right now the area beyond this is 11.5%. Okay, and if I move my alpha value, okay, you can see my z of x bar is moving here. So what I'm doing is I keep changing my the z-score for my sample mean in that case. So as the z-score for my sample mean gets larger, further away from what I would assume the actual true mean to be, the area on the tail gets smaller, right? I'm getting further and further away from what I would assume to be true. Okay, and so as you can see, what happens is that this probability gets smaller as my test value gets further away. So basically, as my my x bar, my sample mean, gets further and further away from what I would assume the true mean to be, my probability basically goes to 0, right? 10 to the negative 4, that's basically 0, and it just kind of bounces back and forth, right? So if it comes back this way, it gets larger, okay? We have different alpha values. If I have alpha of 10%, this area in the red is my critical region, okay? So my critical region, my rejection region, means that if my z-score falls in this area, I would reject the null hypothesis. My sample value of A, if I land in here, okay, if my x bar, if my mean value for my sample is too far away from what I'm assuming my mean to be, then most likely what's happening is that the sample I got is bad because my null hypothesis is incorrect. What I'm assuming to actually be my mean is probably not my mean, because if I get a sample mean, my sample, the average value for my sample should be pretty close to what I would assume the population sample to be, the population mean to be, right? That's the whole reason I get a sample in the first place, because I'm assuming that my sample is a good sample and I can use it to talk about my population, right? But if my sample mean is really, really far away from what I'm assuming my population mean to be, then either I have a bad sample, but if I collected my sample randomly, more likely to be what's wrong is that my assumption about the population mean, H naught, is probably incorrect. So if my z-score for my sample mean is far away from what I assume the population mean to be, then I can probably rely on my sample and say that my assumption about my population is incorrect, and it's probably larger than what I think. That's why this is so far away. Same thing if it was on the other side, it would be too far away. I would think that my population mean should be lower. There should be no reason for my sample to have an average value this far away from what I'm assuming my population mean is. Okay. Now, if my z-score for x bar, meaning that my sample mean is not in the rejection region, okay, we can even bring this a little bit closer, okay. If it's over here, it's green, you can see, it's close. It's close enough for me to assume that there's nothing fishy going on, okay. This is my cutoff point. Anything beyond this, I'm saying is a bad sample, either a bad sample or I have a wrong assumption about my null hypothesis, okay. And so we have different levels of alpha. If my alpha is 10%, that means I want to make sure I'm pretty close to what I assume to be my population mean. If I stray too far from that, I'm going to say that my population mean is off. Okay, so that's a 10%. If I have it at 5%, it means I'm letting my sample stray away from what I'm assuming to be the true population average value even more. I'm giving myself more wiggle room. Okay, my sample has to be really, really bad, way over here, right? Way over here for me, way over here for me to assume that my population mean is wrong. Okay. When I test at the 10% level, it means I have to be really, really, really far away from my assumption. Okay, if my sample value brings me way far away, that's when I can say, hey, this thing is not right. Okay, but I'm giving myself a lot of wiggle room in order for my sample mean to be somewhere around here. Okay, and so remember, we're using z-scores for all of these, but we can use this with data values as well. Okay. So if I let this play right here, I'm giving myself a lot of room before it's not going to work, right? My probability has to be really, really, really small, smaller than my alpha value in order for me to say my sample or I'm sorry, my population mean is incorrect. Okay, that's what we're doing. That's what the graph is for. I should be able to look at a graph and say exactly what's happening, right? Here, my sample is, it's in the green. It's okay. I'm only giving myself a very small probability window for me to say that my population mean or my population proportion is incorrect.